Marcin, yes.
Okay, so the next speaker is Marcin Kurpas from Poland. Welcome, Marcin.
Okay. Good afternoon, everyone. At the beginning, I would like to thank the organizers to let me share my recent results with this nice spintronic community. And the results I will show were taken were obtained with collaboration with Paolo. You already know because he was the chairman of the morning session. With Martin Mitra, who is giving a talk tomorrow, and with Jaroslav, who is one of the organizers. So tomorrow, sorry, where I should. Okay, don't. Okay, a word of motivation why we should bother about spin-orbit coupling and spin mixing, and what is spin mixing. Actually, after today's talk by Stefan Roche and Roald Kawakami, I think this is not really needed to justify why we should study these effects, because of spin relaxation, and as Stefan Roche said, we love spin orbit coupling in terms of effects like spin Hall effect and so on and so forth, but we hate it because it causes spin relaxation. And there is of course several mechanisms of spin relaxation, and those two mechanisms are usually being said to be dominant in two-dimensional materials which are not heavily doped by for example, holes, there is no magnetic impurities, and so on and so forth. So I will mainly focus on those two, but initially my talk was not related to spin relaxation, but after today's discussion in the morning and this nice, let's say, exchange of opinions about anisotropy, and so I decided to modify it a bit. So let me bring once more the features of the Elliott-Jaffet and Dyakonov-Perel spin relaxation mechanisms. So we had this introduced already today. So in the Elliott-Jaffet mechanism, the spin relaxation rate is proportional to the momentum relaxation rate and Fermi surface average of spin mixing parameter B squared. In the Dyakonov-Perel, so the more scattering, the more momentum scattering we have, the more spin scattering we have. In the Dyakonov-Perel mechanism, we have the opposite dependence. So the more momentum scattering we have, the less scattering, the less spin scattering we have, because of the what we know as a motional narrowing. So the momentum scattering does not lead to, prevents this randomization of magnetization, and the spin gets stabilized. And as we have been already learned today, so in the Dyakonov-Perel, the characteristic thing about the Dyakonov-Perel mechanism is that the spin being in plane with the two-dimensional sample relax twice slower than spins being injected perpendicular to the two-dimensional plane. And can we say something about how it looks like in the Elliott-Jaffet mechanism, which is related to the intrinsic spin-orbit coupling? So I will try to give you at least answer to one material, how we can find it out. So 2 years ago, we had a nice collaboration with Ahmed Afsar and Baros Ozilmias in Singapore when they measured spin relaxation in few layer black phosphorus. Oh, sorry, this is the crystalline structure. So they did the Hanle measurement, the standard technique Hanle measurement, and here are the two plots. So here's the spin valve plot, and here is the Hanle measurement plot, demonstrating that the spin transport in this material is in fact coherent, and we can observe also those effects at room temperature. And the main outcome from this paper was actually this plot. It's here, the black dots show the spin relaxation time, the black dot shows the spin lifetime, the red dot shows the momentum lifetime. And we see that the spin lifetime really follows the momentum lifetime, right? And if you keep in mind this formula given by Elliott, so we see that this mechanism of spin relaxation should be mainly related to the Elliott-Jaffet mechanism. And what Ahmed then did, he just divided momentum lifetime with by spin lifetime, what it roughly gives us this B squared parameter, and got values of the order 10 to minus 5. So we did calculations from first principles using full electron code, and what we calculated was that b squared for the in-plane orientation of spin, what was measured in the experiment, are almost the same. So it's 0.6 times to 10 to minus 5, which is of the same order of magnitude, which was very nice agreement with the experiment. So that was our motivation to extend the studies to other two-dimensional materials, because no one has done it yet as far, and I think it would be nice hint to experimentalists towards which materials they can go, for example, to applications in spintronics. Okay, so which material did I choose? So here we have group, I cannot get used to this. We have group 14 of the periodic table and group 15 elements. So we can, from all of those elements, we can really make two-dimensional materials. Most of them, I think there is a new paper saying that this nitrogen material is also stable. There is a prediction that it can be stable. And all of those materials made of those elements have a honeycomb lattice structure, which is rippled. So there is a lattice deformation in the z direction, of course, except graphene. And all of them have inversion center. So it means that in theoretical calculation, we extract this b squared, which can be related to spin relaxation in the Elliott-Jaffet mechanism. So let me now introduce the outline. I mean, let me now say what the outline. So at the beginning, I would like to say about spin orbit, few words like a recap of the spin orbit coupling and define the spin mixing parameter. Then I will talk about intrinsic spin orbit coupling in graphene once more. I will try to justify why this is important to redo this Hamiltonian. Then I will go to the rippled graphene-like materials and show numerical results, and then I will conclude. So if we take the Bloch state of an electron in a band n at the k point, so it composes of the lattice periodic function, the spin function, and the plane wave. So without spin orbit coupling, this eigenstate is this spin part is an eigenstate of the spin operator, let's say spin z operator. So once we include spin orbit coupling, due to this interaction, this initial state we get an admixture of the opposite spin, and the strength amplitude of this admixture is given by the ratio of atomic spin orbit coupling divided by the energy distance to the band that contributes to this spin orbit coupling element, matrix element. So if our system has the time reversal symmetry, so then we know that in the Kramer's degeneracy, the time reversal partner of this state will be degenerate, but at the minus momentum. But if additionally the system has the space inversion symmetry, so what we get is that those two degenerate Bloch states in the form I show here have to be degenerate at every k point in the Brillouin zone. So all the bands in all those materials I shown you are always spin degenerate. And then having this written like these two Bloch states, we can define the spin mixing parameter as the unit cell integral of the modulus squared of the admixture amplitude. So this b is very small, much smaller than a. That's why but let's say it's perturbative, and then taking the integral over the unit cell, we define the spin mixing parameter. Okay, and we had today talks about how it is done in experiments, so we can inject spins oriented differently with respect to our sample. So this is my sample here, let's say graphene. Here are the ferromagnetic leads, and we can, for example, polarize this in the ferromagnetic electrodes that the injected spins are polarized out of the plane. So I will call it spin quantization axis, and how it corresponds to the Hamiltonian, how I describe my system is that if we take those two Bloch states which are degenerate, then if I say that my spin quantization axis is along z, so those eigenstates are eigenstates of the sz operator. And now if I take the spin orbit Hamiltonian, then I see that the spin conserving term contains this sz and lz of orbital angular momentum operator, but the spin flip term composes of those two terms. But if I now what we can say from this is that if we take the Hamiltonian which doesn't have the spherical symmetry, So the crystalline structure anisotropy sits here in the gradient of the crystalline potential. So if we make kind of a mapping from a mapping that this angular orbital momentum is an approximation of this of this bracket here, so we can say that this L operator also has stored the information, or the solution of this Hamiltonian also has the information about crystalline structure and crystal anisotropy. Okay, and now what happens if we change the spin quantization axis along x? So we inject spins being in plane. So now those states corresponds to the eigenstates of Sx operator, and the spin conserving term in the Hamiltonian is now Sx times Lx. So you see that the spin part now couples to the different orbital part, but the spin flip term is consists of those two Sz and Sy terms. Okay, so having this set, we can define a more general spin mixing parameter that now we can write those two degenerate blow states with a given spin quantization axis, and if we use this definition, we can give an alternative definition of spin mixing parameter as a 1/2 minus expectation value of spin operator being parallel or anti-parallel to the spin quantization axis. And the main minus here comes when there is the positive spin expectation value. If there is spin down expectation value, it has to be plus. So you immediately see that this spin mixing parameter varies from 0 when we have no spin mixing, as without spin orbit coupling, to 1/2 when we have fully mixed states. Okay, so what information we can extract from spin mixing parameters? So we already know that this is enabled by spin orbit coupling. So to some extent, it should reflect the strength of the spin orbit coupling in the value of this b squared. So as I already showed you, there is an isotropy of the crystalline structure that couples to the spin. So this spin mixing parameter should also reflect the anisotropy of spin orbit coupling in our band structure. And having in mind this Elliott relation, how we can relate the spin mixing parameter to spin lifetime, so we can say how quickly we lose the spin component along the spin quantization axis in experiment. Okay, so let me now start with the intrinsic spin orbit coupling in graphene. So this is mainly dictated by the symmetry of graphene, and the point group symmetry of graphene is D6H. Of course, graphene is flat; it has no lattice deformation. I'm now referring to to perfect graphene. And what is important thing for graphene lattice is the mirror plane here, lying in plane with the graphene lattice. And as a consequence of this mirror plane, is how spins transforms with this symmetry. So if we, for example, have spin Sz, so as an axial vector, we flip the spin and multiply by -1. So spin Sz transforms properly with this sigma h, but spin Sy and Sx, they don't preserve this mirror plane. So what it means that spins in flat graphene cannot have spin x and y components. So spin in flat graphene can only have a z component. And this is the reason why in all these effective models we already also seen today that people were using, the intrinsic spin orbit Hamiltonian has this form diagonal in spin. So we see that there is only a z operator. This is valid, this is sublattice, which already been discussed as Hamiltonian, so I will not discuss it in detail. But what is important here, it's diagonal in spin basis. So the only effect here on the band structure is the opening of the spin orbital gap, but spin expectation values are always 1/2, what means that there is no spin scattering. So there is no spin mixing, and block states are always eigenstates of spin operator. And what is important about this Hamiltonian is that if we include only p orbitals, the spin orbital gap is of the order of 1 micro eV, but if we include d orbitals, then the intrinsic gap here at the k point increases 10 times. So then the spin orbital gap is of the order of tens of eV, or micro eV. Okay, so the question is it the whole story about the intrinsic spin orbit of graphene? And the answer is yes, in terms of gap, but no, in terms of spin physics. So let me now show what we did in our research paper. So we redone the intrinsic spin orbit Hamiltonian from the group theory. So this was done by Paulo. So from DFT we can read out the irreducible representation and then formulate the effective Hamiltonian. And the key features of this Hamiltonian are the following. So without spin orbit coupling, the Dirac cone here is double degenerate. If we include only intraband interaction, so PZ with PZ orbital, as in the effective models I showed you before, the band gap opens here, but the spin expectation values are 1/2. But if we include interband coupling to PX and PY orbitals, we get renormalization of the band gap, and also what we get is that the expectation values of spin operator in the Dirac cone bands are less than 1/2. And from this you immediately see that B squared is non-zero even in flat graphene. So here are the solutions, the exact solutions. So those parts which are being admixed by spin orbit coupling, they come from those low-lying PX and PY orbitals. Okay, so we have non-zero spin mixing parameter, and the question is, are d orbitals also important in spin mixing or not? Because they are essential to get the correct band gap for graphene. And if you take a look in this paper, Sergei Koshu, then he calculated the Dirac cone bands. Here is one band and the other, and you see that they have admixture of d orbitals, which are essential to the band gap. But the only spin orbit coupling, the only matrix element for the spin orbit coupling is also diagonal in spin basis. So what it means that d orbitals do not contribute to spin mixing in graphene. Okay. So the question is now, if we have non-zero spin mixing, can spin relax in graphene, in flat graphene? And the answer is no. Because if you try to calculate the matrix elements for the which couple the momentum, for example, then you will end up with this matrix elements, and this wave function is odd. This if the impurity potential preserves the mirror symmetry of graphene, it's even, and this function is even. So those functions have different parity. So the whole matrix element is even, and we get 0 at the end. So this means that there is, even if Bloch states are now spin mixed, there is no spin scattering in graphene and spin relaxation if graphene remains flat. Okay, and how does the situation change if we ripple our graphene? So we go from graphene to silicon and germanium and all those materials. So then rippling causes the sp3 hybridization, and we get renormalization of the intrinsic spin orbit coupling strand. And new term in the spin orbit Hamiltonian is now allowed by symmetry. So this is the classical. In the effective model, we can write it down as the classical intrinsic spin orbit coupling in graphene. And this is what is called intrinsic Rashba or PIA Hamiltonian, which looks similar to Rashba, but in contrast to the Rashba coming from the external electric field, this Hamiltonian does not cause the splitting of the spin states, because it has different sign at k and k prime. Okay, but what we see, the essential thing is that now we have spin mixing incorporated in our Hamiltonian. Now I will go to the results. So first let me focus on the spin orbital gaps. We extracted it from DFT. So here I plot the band structures of silicon, germanium, and stannine. Graphene I skipped because it's essentially look as in silicon, but the spin orbital gaps are much smaller. So what is the effect of spin orbit coupling? So we know that if there are some degeneracies, so some of them can be removed by spin orbit coupling. For example, here at the K point and here at the gamma point. And I extracted those spin orbital splittings here. You see that they grow with the atomic number. If we go from carbon through silicon, germanium, and stannine, there is a growth both from at the K point and at the gamma point. So these are materials made of group 14. All of them are semi-metals. Now if we add one electron, so we move to group 15, so the band which was now the conduction band, the Dirac cone, now has to be still in the valence band. And the electronic properties of the materials change dramatically because from semi-metallic character, we go to the semiconductors with a sizable band gap. So we see that for most materials here, the maximum of the valence band here is at the gamma point, while the minimum of the conduction band now is between of gamma and m. So we have indirect semiconductors. And the Dirac point is low in energy, 2 electron volts below the Fermi level. So it doesn't really matter for the low energy physics. Okay, so I extracted all those band gaps and collected them and plotted them here on this plot versus the atomic number. So what we get here is that we see that for those 3 curves, we see that the scaling law of lambda of delta SO with atomic number follows really a quadratic dependence. And this dependence is already predicted by Landau and Lifshitz and in this paper, and it is said to be the same as for valence electron in isolated atoms. So now we have solid, we don't have isolated atoms, but what you observe is that the scaling of the spin orbit strength is the same as the atoms were isolated, which is quite surprising, right? Taking into account the complicated things which happen in crystals. Okay, so we also calculated the spin mixing parameter. What I'm plotting here is Fermi surface average, spin mixing parameter versus the Fermi level, measured from the top of the valence band here and from the bottom of the conduction band. And spin quantization axis is along Z, so we inject spins being out of plane to the graphene lattice. So let me now first show, here's the result for graphene. We see that the value is of the order of 10 to minus 7, which is really, really small. If you wanted to translate it into spin relaxation time, you would get, taking 100 of picoseconds of momentum relaxation time, microseconds. So which we cannot explain really the experiment with this, right? But what is important here is that you see that if we change doping, those values don't change. And the reason for that is that we start our Fermi level here. So if we lower the Fermi energy, we go here on this cone, but this does not change because there is no other bands that could contribute to the spin orbit coupling here because all of those bands lie really low in energy. So we can say that spin orbit coupling here is constant in this band. The same happens for graphene, for silicon, for germanium, and then for stannine, the maximum of the valence band is here at the gamma point, which is point of the highest symmetry here. So the spin orbit coupling is really low, it exponentially increases. And once the band at the K point crosses the Fermi level, we have this kink here, and there is additional contribution to B squared. So what we see that if the Fermi surface that crosses, or the Fermi contour that crosses the Fermi energy has another contribution, because of the dependence of momentum of spin orbit coupling, we can have discontinuous change in spin mixing parameter. In conduction band, no such things happen, so there is no another contour or part of the band structure that would contribute to the contour here of the Fermi level, so we observe only just smooth lines. So now if we change the quantization axis, so now we inject spins being in plane, so what we get is, because of the degeneracy of the Dirac point, here we have the spin hotspot, so directly at the Dirac cone, the spin mixing parameter is very, very close to 0.5, so spins are fully mixed, and it exponentially decrease, those curves decrease towards the values given by spin quantization axis along Z. And the same we observe for the valence and for the conduction band. And also, again, we observe a kink here when we cross another band crosses the Fermi level. And for group 15 materials, similar results are plotted here now. So all the kinks here corresponds to the crossing of another band, crossing of the Fermi level of another band, and here this exponential growth of B squared is because the valence band maximum is at the gamma point. So once we are going away from the gamma point, we increase the crystal momentum, and then the spin orbit coupling is getting stronger. Okay, so we ask the question, so if we have a scaling law for the spin orbit coupling strength, will this B squared parameter also follow some power law? And if you try to calculate the correction to the state due to spin-orbit coupling, the correction is linear with the strength of the spin-orbit coupling, but b squared has this parameter squared, so correction to b squared should be lambda SO squared. And as I showed you before, the lambda SO depends roughly as the z to power of 2, so the b squared should follow the z to power of 4 power law. So what we did, we chose the Fermi energy at the 60 MeV from the conduction band here to here is valence band. Sorry. No, this is conduction band group 14, group 15. And this was chosen in such a way that there is no spin hotspots or vicinity of the other bands crossing the Fermi level that could increase the value of b squared. So at this Fermi energy, we extracted the values from, we took those values, and plotted them here with the fit. So the points are here, it's the calculated values, and the lines are fits to those values. So what we see here that the b squared scales as z to power of 4.6 for group 14 elements as an atomic number to power of 4.8 to group 15 elements. So, okay, there is a deviation from z to power of 4, but I would say we would naively expect that this should be z to power of 4 because spin-orbit coupling is kind of complicated thing in the crystalline solids. And there are also other effects that we already discussed, and so actually we don't fully can explain really what the deviation comes from because it's really complicated problem, but we can say that roughly it follows the z to power of 4. And now today we had a discussion about anisotropy and how to measure this anisotropy and what it can tell us. So I also calculated the anisotropy of spin relaxation into out of plane, and this is plotted here. So we see that if the Fermi level is close to the Dirac point, then due to this spin hotspot we have the very high anisotropy, but it decreases if we go away from the Dirac point, if we lower the Fermi level or increase in the conduction band. Now if you remember what was said today, that in the diagonal parallel mechanism, the anisotropy of spin relaxation in plane to out of plane is 1/2. But if you take a closer look at this blue curve, which is plotted for graphene, you see that b squared for in plane is 1/2 of b squared of the out of plane spin orientation. So if we take this Elliott-Jaffet formula and for example, and see that this spin relaxation rate for a given spin quantization axis is given by the spin mixing parameter parallel to the spin quantization axis, you would get that spins in plane would relax twice slower than spins being out of plane. So you would get the same dependence as for the diagonal parallel mechanism. I told you at the beginning that in flat graphene, spins don't relax. But if you break this mirror symmetry, but small rippling, for example, then we can enable the Elliott-Jaffet mechanism. So I would say it's really surprising that we observe the same kind of anisotropy for intrinsic spin-orbit coupling as for the extrinsic one. Okay, and we ask the question, can we really understand it? Where does it come from? So here I plotted here I show the orbital character of the band structure of graphene. So we see that the Dirac cone is of PZ character, and those bands are mixture of px, py, and s orbitals, but here is also px and py. And now, what I'm plotting here is actually the b squared plotted along the high symmetry lines of graphene for the valence band of the Dirac cone. And what those lines correspond to, here the black label all means that all those matrix elements for the spin-orbit coupling are taken into account. And I'm switching off the individual contributions here. So when it's written no SZ, it means that this term is switched off from the Hamiltonian. If it means no SX, it means that this term is switched off, and so on and so forth. So here the black line gives us this 10 to minus 7, let's say. Here we are focusing only close to the Dirac, to the K point, right? Because there is the Fermi level. So now if we have all contributions, we have the solid black lines. If we switch off the SZ, this one that couples px and py orbitals, no difference, no changes. But if we switch sy or sx, the b squared changes dramatically, and what we see is that the contribution from this spin matrix element and spin matrix element here close to the K point is equal. And if we change the spin quantization axis, so now the spin quantization axis is in plane along X, so we again, now this X is a diagonal in spin, right? So it should not cause any spin flip. So here all elements are present here, so you are switching SX off, which should be diagonal in spin, no changes. You are switching off SZ, no changes, because SZ couples Px and Py orbital, which don't couple to the Pz orbital of the Dirac cone. And now we are switching off Sy, spin mixing goes to 0. And the same will happen for spin quantization axis along Y, only Sx operator contribute, this matrix element with Sx coupling Pz and Py, contributes to spin mixing close to the Dirac cone. And now what we can say that the anisotropy, which I showed you, this B squared being parallel to the lattice, perpendicular to the lattice close to 1/2, is a consequence of the sp2 hybridization of graphene orbitals. If there were coupling between Px and Pz and Py and Pz, we would not observe this 1/2 ratio. Okay, and one more slide, because there were some discussions about anisotropy. So here I have two materials made of the same element. One is black phosphorine with this Packard structure, second is blue phosphorine. There are single layered materials, there are different band structures, and here is this Fermi surface average B squared for the valence band, conduction band, valence band, conduction band. So what we see here at the gamma point, we have no degeneracies really close to the Fermi level. So the values are of the same order, and there is really not drastic changes to this B squared. Also in the conduction band, because here we only one band, let's say, contributes to B squared. But if we check the B squared for the blue phosphorine, we see that for the valence band here and spin quantizations being, let's say, in plane, we have dramatic changes, few orders of magnitude to the B squared. So not only the direction of spin quantization axis contributes to spin anisotropy, but also the crystalline structure itself, which can be somehow a hint to the experimentalists which we should choose. Okay, so with this I would like to thank you for your attention, and I will not read the conclusions because it's already out of time. Thank you.
Thank you, Marcin. Questions?
Hi. In the last two materials, do the group symmetry change from one to the other? Which one is each one, please?
So this is D2H, and this is D3D. Sorry, the opposite. Black phosphorus is D2H at the gamma point, and blue phosphorine is D3D.
More questions?
So the conclusion here with respect to the anisotropy of the taus is really that then you cannot really tell them apart experimentally without actually looking at in more detail in terms of the band structure. So there's no simple explanation in this sense.
So I would say this is a bit provocative that we can relate this B squared to this, and because what we also need to the Elliott-Jaffet mechanism is the anisotropy of the momentum relaxation times. So the anisotropy of tau is basically a product of anisotropy of B squared and anisotropy of momentum relaxation. But I don't know if this answers your question, because I don't know if I got it correctly.
You know, if I just look at the 1/2 number, doesn't mean anything. I cannot tell which one is which.
I would say no. I would say that, so what I can say that if you take this 10 to minus 7 value of B squared and calculate the spin lifetime for graphene, it should be of the order of microseconds. And we know that for Rashba, it should be slower. The relaxation should be faster. But there is one more thing that I talked to Ahmed and asking experimentalists what's the fluctuation of the Fermi level in graphene. And this is of the order of tens of milli-electron volts. And I showed you here I showed you here that there is a spin hotspot if we inject spins being in plane. And then if you take an average with some, let's say, over the energy range, then this could contribute really highly to the spin relaxation. And actually one would have to calculate and compare the Dyakonov peril and the Elliott-Jaffet, because here close to the Dirac point, the Elliott-Jaffet can be really contributing to spin relaxation, I would say. But then you see that this ratio is not 1/2, because the ratio of the anisotropy is then 10⁶, let's say, into out of plane. But the same would happen for Dyakonov peril, because there is also spin hotspots in Dyakonov peril. So I would say they would follow the same dependence. So you would not be able to distinguish, as you said, which one is which.
But what if you look at the temperature dependence of the ratio?
Okay, then that's the key, I would say. That how it follows the momentum relaxation time, then you could distinguish from these basic formulas I showed, right?
Okay, I have a related question. What if you break a symmetry with electric or piezoelectric fields? Can you distinguish between them?
No, I mean, in the experiment that would be difficult. So I would say the only what Carlos said is the dependence, how they follow the momentum relaxation time. But I would say it's always complicated, even for experimentalists, right?
Okay, one more question.
Marcin, what's your definition of the spin hotspots? Because I'm slightly confused. So seeing your graph.
Yes, this one?
No, yes, that one. So I'm seeing something 10 to the power of 6, and on the slide, which will come now, you show that the T parallel versus T perpendicular squares or scales as a B square divided by B square, and you say that
sorry,
it should be something like 1/2. So I'm slightly confused.
Okay, here should be T2 minus 1. This is what you mean, right? Sorry. Because what I'm showing here is not, I'm here in this formula, I neglected this part of this, because here we have spin hotspot for spins being in plane. So what this formula is about is if we dope graphene, and now here this is about 1/2. So this ratio here, for a moderate doping, I would say.
General definition of the spin hotspot.
Spin hotspot appears when you have degeneracies in your band, and then, for example, for graphene, you have spin being the only spinning component is along the z direction, and now if you inject spins being in plane, then they have to. I would describe them as a. But okay, I would understand by spin hotspot enhancement of B squared, that it jumps to 0.5 due to accidental anti-crossings or degeneracies or Brillouin zone edges.
Okay, more questions? Well, if not, let's thank Marcin again.